Hello and good evening, everyone. Hope you guys are able to hear my audio. We'll just be starting in just a while. I'll just hang on for just 1 or 2 minutes and then we can start. So, in the meanwhile, I'll just share my screen and please do let me know if I'm audible and if my screen is visible. So, is my screen visible? Are you guys able to see the presentation?
Yes, sir.
Okay, thanks. Yeah, I'll just start. I'll just wait for a minute and then we'll start. Okay, so good evening once again, and I'll just start now. Why the video is not appearing, but anyway, okay. Welcome to week number 2 of the problem solving session for the course on power electronics with wide bandgap devices. So I am Nand Kishore from Department of Electrical Engineering, IIT Delhi. So in this week, you read about fundamentals of dynamic characterization, mostly using what is called the double pulse test. We'll just have a very brief recap of what is a double pulse test, right? And then how do we achieve or how do we perform DPT or double pulse test as it is called on the device. So we have to use a gate driver through which we will generate appropriate pulses so that the device turns on and off, right? So then you guys also studied about what are the essential features of a gate driver, what are the functionalities of a gate driver, and how do you design it, right? And once you saw what a gate driver does, you also read about some of its auxiliary features, but very important features, they are protection features, right? So most of the commercial gate drivers that you will see in markets today will feature most of these protection features, right? Okay, so the protection features you just started about UVLO, or what is called as the under voltage lockout, right? You studied about UVLO and you also studied about overcurrent protection, right? So both of these are very fundamental protection features, and kind of they are available in most of the commercial gate level ICs that you will get in the market. Okay, so based on these, we will see some problems, and most of the problems, as you can understand over here, are mostly they are theoretical problems. So before we jump into that, we will just see a very brief recap, and we will go through the theoretical problems. So apart from these theoretical questions, from probably the next week or so, if we are able to complete this set of problems, we can see a bit of numerical problems as well, right? So yeah, we'll just go into problems today. Okay, so in this week you started off with what is called the DPT circuit, or the double pulse test circuit, right? So this DPT circuit is also sometimes called as phase leg test setup. Okay, so because you can understand that if let's say you take an inverter, right? You say you take a three-phase inverter. I'm not drawing the, okay, let me just draw one device. So you take the inverter A, B, and C. So you see that each of these legs, right? So each of these legs represent one phase of the inverter, correct? So this is phase A, and this is B and C, right? So that is why you can call this as a phase leg test setup, because what you have essentially over here, so this is basically just a DC source and then two switches in this fashion, right? And you have an inductive load which is connected across the top device, correct? So this is also called as a phase leg test setup, or this is also called as a clamped inductive load setup. Okay, because what you have over here is a pure inductive load. This is the load inductor, and kind of it is across the directly connected across the top device. Okay, so yeah, so the point is the DPT setup is also called as phase leg test setup or clamped inductor load setup. So all these names are interchangeable. But what is the essential purpose of this DPT circuit, or what do we do with this circuit, right? So that is what we want to study. And before we go further ahead, why are we using this kind of a circuit? Why are we using a DC source, and then you have two switches like this, and then you have an inductor connected across the top device, right? So if you let me take a new slide over here. Insert slide. Okay. So let me redraw the circuit for ease of understanding. So you have a device over here. Okay. So, okay, so let me use some other name. A and B might be confusing, right? So let me use Q1 and Q2, and this is VDC, and this is the phase point, right? Or the switching node as we call it. Okay, so as I was telling previously, this is called as the phase leg test setup, right? So this is your phase leg test setup. But why at all do we have to use this setup, right? So that begs this question: why at all do we need to use the setup? Correct. So you take any converter in power electronics, most of the converters. So all of these are based on half bridges, right? So this is also called as a half bridge circuit. Correct. So let me go over here and just restate that. So this is also called as half bridge circuit. correct? So if you take any circuit, right, in power electronics, mostly so we start with what is known as the buck converter, right? Then you have boost, then you have buck boost, correct? So all of these are kind of non-isolated converters. And in isolated converters as well, uh, you have converters such as um, what is known as the phase shifted full bridge. Okay, if you don't know what is PSFP, no worries, you might study that in higher level or master's level courses. But point is, you have what is known as a phase shifted full bridge. Phase shifted full bridge. Okay, and another such example would be what is known as the dual active bridge. Okay. So you have what is known as the dual active bridge, or DAB as they call it. So dual, you have dual active bridge. Okay, and so on. So you have a lot of circuits. So you have a lot of variants in PSFP. You have a lot of types of DABs and so on. And all of these are isolated. Okay, isolated as in like you have a transformer in between. Okay, so all of these are isolated DC. Okay, these are non-isolated. Okay, so uh, so you have what is known as a push-pull converter, and yeah, okay. So now the point is the common link that connects all of these circuits. If you go into the circuit topology, you will see that what is at the heart of all of these circuits is this half bridge. Okay, so and these are all DC-DC converters. If you take AC converters, right, or inverters as we call it, DC to AC converters, so you have the half bridge inverter. So you have half bridge inverter and then full bridge inverter, correct? Or the voltage source inverter as we call it, full bridge VSI, correct? And in that you also have variants, that is you call them as you can have single phase or three phase and so on, right? So all of these are inverters and these are DC, AC. Okay. Now what links all of these 8 converters together is that all of these are typically made up of this half bridge that you see. Okay. So for instance, if you want to realize a buck converter, right? So some of you might have studied that buck converter looks something like this. You have a switch over here, you have a diode, and then you have the inductor over here, the capacitor filter, and then the load. Correct? You can also redraw this. You can also redraw this as something like you have a switch over here, and you have a diode over here, and then you have the inductor, and then the resistor. Right? So can you now relate to this figure over here and this figure, right? Because both of these figures are just exactly the same. You have the MOSFET, same MOSFET over here. This diode can also be realized with a MOSFET because anyway the MOSFET has anti-parallel diode over here. And then you have the inductor, correct? So this is your buck converter, right? So you see that essentially the buck converter is again made up of a half bridge circuit. Okay. And let's say you take a boost converter, correct? So in a boost converter, it is quite easy for you guys to remember that in a boost converter, the filter inductor is going to come towards the input side. So just the same circuit is going to become something like this. Okay, correct. So you have um, the inductor over here, right? And then, okay, I'm sorry, I just made a small mistake. So you have the inductor over here, right? So this is the same boost converter that we study, right? So you would have studied that the boost converter looks something like, so this circuit is nothing but the redrawn version of this one over here. Okay. So this is the redrawn version of buck and boost. So you can understand that irrespective of whether it's a buck converter or boost converter, what is at the heart of this is basically a half bridge. So this half bridge is the one that is kind of transforming your voltages, that is either bucking it down or boosting it up, right? So like that you can do for buck boost converter as well. Okay. So you see that again, what comes into play is this half bridge circuit. Correct. So let's say you take an inverter, right? So let's go to this case. I'm not going into the isolated DC-DC converters because probably they are out of scope of this course. But if you take a half bridge inverter, right? So what is a half bridge inverter? Uh, Let me take, yeah. So what is a half bridge? So what is a half bridge inverter? Probably cannot write on the top. Okay. So half bridge inverter is going to look something like, again you will have a half bridge over here, and then you might be having the load across this. Correct. So this is the switching node, and if you take the full bridge inverter, correct, what you are going to get is, again you will be having another half bridge, and then you just connect the load directly. Correct. So again what you see is that the heart of this converter is again a half bridge over here and then a half bridge over here. So using this simple half bridge configuration, you can realize almost all the converters in the or you can realize almost all the converters, right? In that you study in power electronics. So the idea is, if you are able to characterize the devices, right? So the basis of performing a double pulse test is to characterize the devices. That is to understand how the device operates or functions, right? So if you are able to characterize the devices in a hybrid circuit, as shown over here, you can expect that the device behavior is going to be somewhat similar if the conditions are same in a power electronic converter as well, right? That is, if you are able to replicate, or if you observe some switching behavior of the device in a hybrid circuit, you can fairly estimate that the device might behave in the same way if it is used in a buck converter or a boost converter or an inverter or so on. Okay, so you understand that since the half bridge is the core of almost all the um, converters, the devices are characterized in a half bridge configuration. Okay, fine. So I hope this is clear now. Once if this is clear, you can of course interrupt me if something is unclear, but if this is fine, we can just go ahead into double pulse test. Okay, yeah. So what is this double pulse test, right? So this is the same DPT circuit redrawn over here. That is, you have the plus DC over here, correct? And then you have Q1 and then Q2. So there are two devices over here, Q1 and Q2. You have the inductive load connected across Q1, right? And then you are feeding the gate pulses to Q2. Okay. So what is a double pulse test? Basically, you feed 2 pulses to Q2, right? Or we call it as the DUT. DUT means the device under test, if you know, right? So DUT is basically device under test. Okay. So what we do is we want to characterize Q2. That is, we want to understand the switching behavior of device Q2. That's why we call it as a DUT or device under test. So over here, what you do is if you want to characterize a particular device, first thing that you do is you connect the load inductor across the complementary device. In this case, we want to characterize the lower device Q2. Therefore, we connected the load inductor across Q1, right? And what we do is in a double pulse test, obviously, you feed 2 pulses, 2 very small time duration pulses as shown over here, right? So initially the device was in the off state, correct? It was off state. And then what you did at this particular instance, you turned it on. So VGS is the voltage across here, right? Voltage across the gate to source of Q2. So what happens? Your VGS basically increases from VEE to VCC. That is, you're turning on the device above the threshold voltage. Okay. So you made VGS go from VEE to VCC, right? That is basically you turned on the device for some particular duration, right? And then what did you do? After some duration, you again turned it off. And then again you turned it on, right? And then you turned it off forever. That's it. So this is only a double pulse test. That is, only 2 pulses are going to go to the load inductor, to the device Q2, right? So you turned off the device, then turned on it, then turned it on, then you turned it off, and then again you turned it on, right? So this is your double pulse test. And the idea is we want to do device characterization. That is, we want to understand how the device is going to turn on and turn off, right? So we are more interested towards understanding what is happening during this turn on, turn off duration, what is happening during this turn on duration, what is happening during this turn on duration, and what's happening during this turn off duration, right? That is, we want to understand how the device turns on. Okay, so at this instance, I turned on the device. From it was initially in off state, I turned it on. So how is the device going to behave? At this instance, I turned off the device. That is, the device was on, it was carrying some current, and I suddenly turn it off, right? At this instant, I again want to see how the device turns on. In this instant, the device previously it was carrying some current, right? So when I turn on Q2 again, how is the current going to transfer to Q2, right? Is it very smooth, or will it have transients, or what kind of transients if it has, and so on, right? So we want to understand what's happening during these minute switching behaviors, as we call it. Okay, and that's the purpose of a double pulse test.
Hello.
Yeah.
Sorry for just one small doubt. If I
Yeah.
in the half bridge, if I use any GaN-based MOSFET, so in that
Correct.
case also, should I give this negative gate voltage for turn off, or I can make some 0 to VCC?
See, yeah. So, good question. Just a second. I'll just. So for GaN devices, if you see, okay, so let me take this. So mostly for GaN devices, okay, so before I go on to GaN devices, so generally the VCC and VEE that you see over here, right? So let's take some numbers so that will make us understand better, right? Yeah. So point is, in any generic device, right, in any MOSFET, right? So there would be some threshold voltage, and you expect that since we are mostly dealing with in-channel enhancement mode devices, V threshold is going to be positive. V threshold would be positive. So the idea is, if we want to turn off the device, we bring the gate source voltage below V threshold, and if we want to turn on the device, we bring it above V threshold. Okay. So generally, So the threshold voltage, let's take some numbers. So let's say the threshold voltage is somewhere around 3 volts. Okay. So the idea is if you go below 3 volts, the device will turn off no matter what. And if you go above 3 volts, the device will turn on, right? But point is generally while driving the device, we never give, okay, so let's say the threshold voltage is 3 volts. We change VGS from 0 to 3 or something, right? So what we do is we generally have somewhere between -5 to +15 volts. Okay, generically. So if you take SI devices or even SIC devices, we generally have gate source voltages ranging from -5 volts to +15 volts. Okay, so when the device is off, right, you can understand that VEE as we call it, it is held at -5 volts. That is why in this diagram as well, let me just erase this off. Oh, okay. Yeah, so that is why over here as well, you can see that VEE is not exactly at 0. It is at a negative value. Okay. And your threshold might be somewhere over here, but we are not driving the VGS at threshold voltage. We are not driving it over here. We are driving it at a much higher value, right? We will see why in just a few slides. But point is to answer your question. Oh, the annotations are gone. Okay, anyway. So genetically, I was mentioning that V threshold is just +3 volts, right? And typically, we drive VGS between -5 volts to +15 volts, correct? And where your -5 volts corresponds to VEE and +15 corresponds to VCC, right? And this is mostly the case for silicon carbide devices or even IGBTs. Okay. And depending on the manufacturer, this negative voltage can vary, right? So some manufacturers tell that it's better to give -3 volts, and it can be between +15 to +18 volts, +20 volts as well. Okay. So yeah, you understand that VEE is typically going to have a negative range, and VCC is going to be between +15, +18, or +20, something like that. But this is for SA and SIC and IGBTs. However, for gallium nitride devices or GaN devices, as we call it, right? So, okay, so let me just again. Okay, so in GaN devices, you guys read about it in week number 1. You have devices which are in cascode configuration, right? And you also have direct E mode GaN, correct? So the idea is if you see GaN as a material, right? If you try to analyze its property, you see that GaN will naturally give you a naturally on characteristic. Okay, naturally on means even if you don't apply a positive gate source voltage, the channel is going to be on. Okay, that is naturally if you see, right? So I'm just going into a bit of device physics. I know I'm just deviating a little from the problem, but it's good for you guys to know. So GaN devices they are actually naturally on. Okay, GaN as a material, if you see, right, it is naturally on, which means that at V threshold equal to 0 volts, channel is ready to conduct. Okay. So you obviously understand that this is something that we don't want, right? So as a power electronic engineer, we want to operate the devices as a switch, right? We don't operate the devices in the linear region, I mean, or in the saturation region. So we want to operate the devices as a switch that is on and off. So I want to control when the device is going to turn on, or naturally it should remain turned off, right? So in order to make the GAN devices naturally off, right, people came up with a number of theories or number of alternatives, but two of them are commercially adopted and they stand out. So one is known as the cascode configuration, and the other one is the E-mode GAN configuration, right? Okay. So in
This
cascode,
emote, hello.
yeah, yeah.
Yeah. This emote GAN is basically this direct drive GAN you are telling, huh? Or these both are different.
No, direct drive GAN is a bit different. Yeah,
The
I
direct
didn't
drive
go into
GAN,
it.
I think it is not normally on device, no?
No, direct drive is also not normally on, but the principle is something similar to cascode. Okay, not
Okay.
exactly the same, not exactly the same, but principle is something similar to cascode, wherein what you do is you have an SI MOSFET, you have an SI MOSFET or a silicon MOSFET. You understand that silicon MOSFETs are going to be naturally off, right? So silicon MOSFET kind of controls your GAN conduction, correct? So what you essentially do is you are giving the gate pulses to the SI MOSFET. Okay, only if the SI MOSFET turns on, the GAN can conduct, right? So this is what is known as a cascode configuration, right? So kind of in series, you have the silicon MOSFET. However, E-mode GAN, or the one that is mostly used nowadays, right? Because you understand that if you have a silicon MOSFET, again, the silicon MOSFET is going to take some time to turn on and turn off, and we don't want that to enter into or that to dictate our switching characteristic. So a better option would be to use E-mode GAN. So what people did in E-mode GAN was, right, so we will just go back into a bit of device physics over here. That is, you have N-channel devices and P-channel devices, correct? And during conduction, when the channel forms, it means that the channel has completely formed, means there is no depletion region in between, right? So there is a free path for the charge carriers to conduct. So what people did was they introduced a P-GAN layer is introduced in the GAN channel, GAN conducting channel. Okay. So the P-GAN is basically responsible for creating a depletion region, right? So what you do is when you give the gate source voltage, you are actually controlling this P-GAN and not the direct channel, right? So basically, if you allow a depletion region to form using this P-GAN layer, then the GAN and GAN HMTs are going to turn off and they are going to turn on. And this is widely adopted nowadays. And just for information, this cascode configuration is being manufactured by a company called Transform. Okay, and this E-mode GAN is being manufactured by a company called EPC and a company called GAN Systems. Now it has been bought by Infineon. Okay, so these are just some names of companies, and um, based on their recommendations, coming back to the question, the gate source voltage changes. Okay. Now you understand that for cascode GAN, it is quite straightforward because you are having a silicon MOSFET to control the GAN conduction, and basically you give the gate source pulses to the silicon MOSFET. So what will be the VGS? Your VGS is going to be between 0 to plus 15 volts or minus 5 to plus 15 volts. You can see this in the data sheet, they generally specify. Okay. However, if we come to E-mode GAN, that is, you have EPC and GAN systems which manufacture that. So if you come to E-mode GAN, so EPC recommends using a gate drive voltage only between 0 to plus 5 volts. Okay, so that is 0 is the VEE and plus 5 is the VCC. Okay, so 0 is the VEE and plus 5 is the VCC. They don't recommend any negative gate drive voltage. And if you go to GAN systems, they generally recommend between 0 to plus 6 volts or minus 3 to plus 6 volts. Okay. Now it is based on the user's requirement or discretion as to whether they want to use a negative voltage or they want to use 0 as VEE. Right. In either case, whether it is VEE or VCC, whether it is VE or whether the VE is 0 or minus 3, right, the device is going to be off. Because for GAN HEMTs, the threshold voltage for E-mode GAN, right? Yeah. So for E-mode GAN, the V threshold voltage typically is around 1.6 or 1.7 volts. Okay, it's around 1.6 to 1.7 volts. So if you go below 1.7 volts, you're safe. Now the point is for EPC GAN, the manufacturers specify between 0 to plus 5 volts. That is, it's the recommended value. And for GAN systems on Infineon GAN, you have between 0 to plus 6 or minus 3 to plus 6 volts. Okay. Is it fine? Does this answer your question?
Yes, yes. Okay, thank you. I'll go through once the
Okay.
data sheet.
Yeah. So now the point is, it is up to the designer, right? It is up to the designer whether they want to use 0 or whether they want to use minus 3. Okay. So just to make this session a little interactive, can anyone tell like how to decide whether to use 0 volts or minus 3 volts or anywhere in between as well? It's fine. You can. It's not that it's a hard and fast rule. It needs to be minus 3. Let's say you give minus 1 volt or minus 2 volts. It's fine. You can give any voltage range. But how do you decide whether you want 0 volts or minus 3 volts? Any suggestions or any idea?
Sir, if we use negative voltage, false turn on will we can eliminate. So in that case, we can
Correct.
use.
So, correct. So false turn on, in order to mitigate false turn on, we generally go for negative voltages. Okay. So now let me give you two scenarios, right? So that you get a better idea. So let's say my first application is that VDC is basically 400 volts. Okay. And second application is VDC is 70. So VDC is 72 volts. Okay. And let's say in this case, the switching frequency of my converter, any converter, right? Let's say you take a buck converter. Okay, let's say we take a buck converter. Okay. So the switching frequency at 400 volts is, let's say I switch it at 100 kilohertz, or let's say I switch it at perhaps so let's say I switch it at around 200 kilohertz. Right? And over here, I am switching it at 20 kilohertz. Okay. So these are two scenarios. Okay. So, and let's say over here, so let's take two devices, right? So I will just take two different commercially available devices. So it will be more interesting, right? So this is a GAN systems device. Okay. Let's say you take GS6 6516T. So this is a 650 volts rated, right? 60 amperes rated device, rated for 650 volts and 60 amperes, right? and I don't exactly remember its capacitance values, but just for discussion's sake, let me tell CISS is around uh, 2000 picofarad, right? COSS is somewhere around 650 picofarad. I'm not exactly able to recollect. Okay, so somewhere around this. And let's say over here, this is an EPC device. So EPC, I am not able to exactly recollect the part number, but it's an EPC device. So, and it is rated for 150 volts and 130 amperes. Okay. Current rating is double and the voltage rating is very less. Okay. And the CISS values are more than double. So let's say this is around 5000 picofarad. Okay. And COSS is somewhere around, let's say 1300 picofarad. Okay, so are you guys able to understand it? I have given you two scenarios, right? So one is at 400 volts application, the other is a 72 volt application, right? So you might ask, where do you get 400 volt application? So it's a classical example of onboard chargers in cars. Okay, onboard chargers that you have in cars, they might have the battery voltage changes around 400 volts, somewhere around 400 volts, right? And if you see this 72 volts and 72 volts application, so it may be somewhere in, let's say, e-rickshaws, e-scooters, correct? So, or let's say you have data server applications, data servers, etc., auxiliary power units, etc. Okay, so these are the applications, right? So I have given you totally different scenarios, right? And let's say the power is somewhere around, for this application, the power is around 3.3 kilowatt. It's a classical power rating, and over here the power is 5 kilowatt. So are you understanding it? I'm giving you two test cases and also giving you the GAN devices. Okay. Now can you tell me what should be the VE according to your opinion, right? I'm sorry, it should go back over here and yeah. What should be the VE? Should it be 0 or should it be a negative value? So what should you use and in what case and why? So are you able to understand the question? It took a bit of time just to explain the question, but are you able to understand it? Question is, I have basically given you two scenarios. One is for a car charging application at 400 volts, right? The other one is, let's say, a data server application at 72 volts. Okay, I have given you the switching frequencies. One is at 200 kilohertz, 400 volts. The other one is 72 volts and 20 kilohertz. Okay, and the power rating is also given, right? And the device capacitance values are also given. So from this, can you tell me where you should use a negative value and where do you think, okay, negative value is not required? There is no harm in using negative value, but where do you think negative value may not be required, voltage may not be required?
I think in second case for EPC for 20 kilowatt switching, they are actually the time period will be more, so the CDD have enough time to means leakage to shoot up the voltage in from drain to gate side, and there is a high chance the device can be on in false turn on case. So there I think we should use negative gate voltage to actually false reduce the false turn on case.
Okay, so are others understanding it? Can you repeat once again in a slower fashion so that just for the benefit of others?
I think in the second case where 20 kilowatts frequency is there, switching frequency, as because of the gate to drain capacitance, it has enough time because the switching period is more. So it has enough time to charge the voltage from drain to gate side, and there is a high chance for device to be false turn on. So in that case, I think we should use negative gate voltage for fully turn off.
Okay, fine. So this is one scenario. And for case number one, is it fine? Like, if is it fine if we can use a zero value for VEE, or should we go for negative value? See, for the second case, even though your frequency is really high, right? Your frequency is really high, so you'll be doing fast turn on and turn off. So what might happen is, because you are having a high voltage over here, that is you have 400 volts over here, what can happen is there can be DVDT issues. Okay, high DVDT, right? And because of this high DVDT, it can cause spurious turn on of the complementary device. Okay, so because of this, we try to have a negative value over here as well. Okay, so generally it is better to use somewhere around -3 to +6 volts. Okay, fine. Okay, so we will go back to the double pulse test scenario, and we were over here. We have two pulses, that is a longer pulse and then a shorter pulse. So what do you expect over here? So when the device turns on, when Q2 turns on, then what would happen? So yeah, so when the device turns on, what would happen? When Q2 turns on, the path would be from DC bus. It would go through the inductor, through the device, and back to DC bus, right? So this is during the first pulse, right? This is during the first pulse. That is why. So what you are actually having over here is, if you draw the equivalent circuit, so you have a DC source over here and then an inductor, and that's it. You don't have anything else, correct? Switch is on. So you have a constant DC. You try to flow a current through the circuit. So what would happen is the current would increase linearly because V is equal to L di over dt, right? So V is a constant DC. Therefore, what would happen to I? I would be basically 1 by L integral V dt. V is constant. So V by L integral T, or V into T over L, correct? So based on, if you have a longer pulse, then the current would increase for longer, correct? And the current would show a linear increase because the voltage is a constant voltage, right? So that is the reason you are seeing something like this. Okay, so what do you do then? So what did you do later on? You just turned off the device, correct? So you turned off Q2. So once you turned off Q2, what happened was immediately the device current fell to zero, obviously, right? Because you turned off Q2, the gate source voltage goes below the threshold voltage, and therefore Q2 got turned off, right? Okay. Then after that, what happened? So Q2 got turned off. So after Q2 turns off, you have a buffer period or off period during which now the inductor current is at this point, right? So inductor current is at this point. Okay. So inductor current now finds a path to freewheel through the anti-parallel diode of Q1. Correct? So it would now freewheel in this path. So slowly, very slowly, the inductor current would kind of decrease something like this. And again, what did you do? You turned on the device once again, Q2 once again. Therefore, again, the inductor current would continue to increase for this particular duration. And then you turn it off, it dies down. So your interest is mainly towards this particular region. Correct? what happens over here and what happens over here during turn on and turn off, right? So this is your classical DPT. I hope you guys are aware of DPT. Yeah, so it is just this is just a pictorial representation of what happens over there. Okay. At this juncture, I'll just ask you to hang on for a few minutes. I will open some experimental results so that you guys can have a look at the DPT result for a GAN systems device, gallium nitride device. Okay. Yeah. So just hang on a second. Yeah, so I'll just share my screen once again. So is this visible for you? Am I audible, please?
Yes,
Yes,
yes, audible.
Okay. Yeah, so you can see over here, this is just for a single pulse, but this is just the characterization result for a gallium nitride device, right? So what I did was over here, you have the gate pulse coming over here. Therefore, what happened was your inductor current ramps up, right? Inductor current is the blue, is the green one, which is ramping up from 0. It increased till around probably 30 amperes, and then I turned off the device, just a single pulse, right? So that's why you can see after it turned off slowly, the inductor current is falling, correct? You can see slowly the inductor current falls. And what happens to the device current? Initially, as you turned on the device, there are some transients, right? And then the device current also follows the inductor current, kind of. It increases till around 30 amperes. And then what you did, you turned off the device. So immediately the device current goes to zero. It has some transitions and then it dies down, right? So this is how it looks like practically. I just wanted to show you guys that. So yeah. This is just the first pulse of your double pulse test. Okay, fine. Okay, so after you guys studied about the double pulse test, you also kind of studied potential failure modes for power semiconductor devices. So you have two kind of failures. That is, you have what is known as a shoot-through failure, or this is also known as a hard switched fault. Okay, HSF that we call it. Hard switch fault, right? Or also called as DC bus fault. Okay, that is wherein you see that somehow the gate pulses of both S1 and S2 are kind of overlapping. Therefore, consequently, you have both the devices trying to turn on at the same time. Okay, which you don't want. So what you are essentially having is something like both devices turning on, so there will be a shoot through directly, and the current would be huge, right? And that can kind of damage your devices, right? So this is one kind of failure. The other one is called load inductor saturation, or you also call that as um, um, highly inductive fault. That is, you consider the same double pulse test scenario, right? So if let's say this current increases by too much, you're keeping on the device on for longer, or if let's say the inductance is somehow reduced, right? So then what would happen is the current would go too high, and that kind of reaches your device current rating. Okay, then again it's a fault scenario, right? So this is one case, or you can have something like the inductance, instead of being like this, the inductance makes your current increase something like this. You understand, right? So within the given time period, let's say your L load, there is some fault in L load. Okay, your L load has reduced. So let me just erase falling. Oh, yeah. So if let's say you understand over here that I is basically 1 by L integral V dt, correct? If your L is larger, if your L is large enough, then I is small, correct? Now let's say if there is a fault in the inductor side or the load side, which makes your effective value of L very low. If your L is low, then obviously I would be very large, right? So even though there is no problem in your pulses as such, your load is causing your current to shoot up too much. Instead of like this, let's say the current increases something like this, and it breaches the device rating. Then also it's a problem, and this is what is called as load inductor saturation or highly inductive fault, HIF. Correct? Okay. So what is the way you will overcome that? You have multiple means to overcome that. First thing is you need to sense the fault, correct? So if it is a highly inductive fault, you will of course have current sensors towards your load side, or this is a simple case of VSI feeding a motor, correct? So you will have current transformers over here, they will sense the phase currents. So phase currents are sensed. And if you see that the phase currents are increasing beyond some particular level, you understand that there is some fault, correct? And you obviously know that since the phase currents are essentially the device currents, directly also know that device currents are going to be somewhat same. Or you can also have the current transformer directly in the leg itself, in the switching leg itself. So essentially you will be measuring the device current. Okay. So this is one way of doing it. The other way is to use a current sense resistor. That is, just add a resistor over here. Therefore, if you sense the voltage across the resistor, V is basically I into R. Therefore, you know the resistance value. Therefore, you will know what is I if you sense the voltage. Correct? If the voltage increases beyond a particular level, again it's a problem. It means that there is some problem, right? Overcurrent. Or you can also sense the device VC is at, right? Or in case of MOSFET, you can sense VDS. So you sense the voltage across the device, correct? And again, you know that when the device is completely turned on, right? When the device is completely turned on, the device acts in the ohmic region, presenting a proper RDS. So if you sense the voltage across the device, VDS is basically I into RDS. So basically, if there is any increase in VDS, you know that current has increased. Correct? Again, so if there is some fault, then your VDS will increase, you know that the current has increased. Correct? Okay. So these are the modes of sensing overcurrents. So can anyone tell why there is a diode over here? Directly you can just sense the voltage, right? That is what they are indicating is you are sensing the voltage across this device between this node to this node. Why there should be a voltage? Anyone? I mean, why there is a diode over here? Why is this diode appearing?
For isolation.
Isolation of what exactly?
Like
Why?
high voltage circuit to isolation means for sensing circuit, low voltage sensing circuit or something.
That is one way. But point is, see, you're right. It is basically for isolation only. So what I'm telling is, so what we are having is essentially the idea is I want to have a voltage measurement circuit, correct? I can just directly have a voltage measurement circuit over here. Okay. Voltage measuring circuit, correct? And this voltage measuring circuit will give me what is your VDS, right? And you know that VDS is basically I into RDS. Therefore, if VDS increases, you know that I has increased, basically, right? Now the question was, why you are having a diode something like this? Correct? Anyone else? Can you try to imagine? Um, are you guys understanding the question? Why you are having the diode over here? Are you able to follow this? Just asking. So is it easy for you to follow? Why are you having this diode is a question.
To
Okay.
avoid
So
reverse
now you
flow,
I'm not audible.
to avoid reverse current flow from the measuring device, if any.
Sorry, to avoid the reverse current flow from
Device, if there is any battery source in the device, to avoid any reverse current flow from it to the
correct. So
switch.
right. So let's jot them down. You're right. So there are multiple options. So multiple right answers. So one was as I think you are Ravidas, right? So one was as he was mentioning, you have to have an isolation. An isolation between the power circuit and see basically these voltage measurement circuits are analog devices. correct? So they are realized using analog circuits, because what you will be doing is kind of this VDS. Yeah, let's say I go to the characteristic. Okay, so output characteristics are not there. So you understand that this VDS is going to be somewhere between 0 to probably when the device is in the, we are talking about VDS is equal to I into RDS only in the device being in ohmic state, right? So VDS may be maximum between, let's say, 0 to 4 or 5 volts, something like that, correct? So you will be having analog circuitry, analog measurement circuitry, correct? So you obviously need to have an isolation between the power circuit and analog circuit. Okay, because the devices that you will be using over here, they may not be rated for your 400 volts or 800 volts DC bus. Okay, that is one. Second one is, as you told, to avoid any reverse current flow from here to here. Right. So that is correct. So you obviously want the voltage measurement circuit to act like just a passive measurement thing, right? You don't want it to affect your circuit behavior as such. Okay. And third is following up on this isolation part. So the third point is that, see, you are measuring the voltage, correct? VDS is I into RDS. Now the point is, when you try to understand when the device is blocking, when the device is turned off, right? And then this device is turned on. At that point, what would happen is the entire 400 volts or almost 400 volts will be coming over here. Okay. So your entire 400 volts is going to appear over here. So during that time, what you would want is, I'm not going into the measurement circuit. If probably if we go into it, you might be able to understand it even better. So what you would want is, so when 400 volts is coming over here, as far as this measurement unit is concerned, right, it will just sense the voltage. It doesn't know whether the device is turned on or turned off. You need to have some mechanism for that as well. Okay, to so when 400 volts is coming over here, it will sense that, okay, so across the device, a huge voltage is coming. Therefore, this being 400 volts is much, much greater than whatever limit you will set over there. Let's say you set 7 volts limit as the overcurrent limit. So if you set that VDS is 7 volt maximum, and if it sees 400 volts, then there can be a false triggering of the overcurrent protection mechanism. Okay, so you don't want that to happen, right? This diode plays a huge role in that. Okay, so I mean, again, we are not going into this voltage measurement circuits, but you understand that this this diode is for that. That is, you don't want this voltage measurement circuit to spuriously kind of give a false trigger of overcurrent mechanism when the device is in the off state. Okay, so to avoid spurious overcurrent protection. Okay. Fine. Okay, so is this fine so far? We have discussed about the double pulse test, and I just showed you a few results. And then we discussed elaborately about what are the voltages for GAN devices. And we took two scenarios and tried to understand why we have to give kind of a negative voltage. I mean, you will understand again why we have to give a negative voltage. It's part of week 3 as well, right? You might be seeing the videos as well, right? And then we understood what are the failure modes of devices. That is, you have a hard switch fault or a highly inductive fault, and then you try to kind of understand how we will sense the overcurrent protection, right? And yeah, okay. So if this is fine, we will
Hello,
just go.
excuse me.
Yeah,
Can you please tell that the partner you have shown now one research paper where they did some testing results in which GAN since they have used
yeah. So the
anything?
GAN systems. It is the same device as the one that I had listed down. This is the part number.
Okay,
I think they have
GS level 6.
GS66508T. This is 650 volt and 30 ampere device. This is what was used.
Okay, but this is, I think it is in production, na? Or it is available now?
Yeah, it is available. It's in production.
Okay.
The company is with
Yeah.
Infineon right now. Okay,
Yeah.
Infineon bought GaN systems, but still they are continuing with the same products. Yeah.
Okay. Okay, I'll go through once.
So, just for out of curiosity, are you working on GaN or you interested in gallium nitride devices?
Yes, mainly I'm working in both this SiC and mainly I'm working in high power front-end electronics. So
Acha, nice.
yeah, that's
Great. Okay, so but one of the drawbacks of GaN is that, or I mean, no, not a drawback. It's just it's still in research stage. Is that you don't get GaN systems devices or GaN devices for voltages more than 650 volts. I mean, I think there is one 900 volt device available, but other than that, you don't have a lot of options, right? So you can safely use them for low voltage applications, still probably around 400 volts. But for typical 800 volt applications or even higher, you still have to rely on SiC devices or IGBTs and so on, right? But GaN systems or GaN devices are a very good option for low voltage applications, right? So even your Apple chargers, Samsung chargers, your laptop chargers, most of them have started adopting GaN devices, right? And that enables your fast charging that you are seeing nowadays. Okay. Okay. So just a comparison in the datasheet characteristics, right? So one more interesting thing that you will observe if you see the datasheet, if you try to compare the datasheet of silicon MOSFETs and silicon carbide MOSFETs, is that okay? So you see over here, this is a variation of your device RDS on drain source resistance with the junction temperature. Okay. So you see over here that see as the junction temperature increases from -50 towards 150, your RDS on is showing a quadratic increase, almost a quadratic kind of an increase for SI MOSFETs. Okay. So it increased from 0.1 ohms to around 0.4 ohms. But over here you see for SiC MOSFETs, the increase is also much lower. See from 0.1 to 0.4, it's around a 400% increase. 400% increase. But over here you see it kind of hovers around 0.1, this is 0.15, and maximum it goes till around 0.2, very small increase. Okay, less than 100%, much less than 100% increase, right? So this is an advantage of SiC MOSFETs, that is that you don't see a huge increase in RDS on, but on the other hand you see that for very low temperatures, still around probably 25 or 50 degrees, you see that there is a negative temperature coefficient of resistance, right? I think I have drawn over it. See, so you see over here that the resistance kind of decreases, correct? And then it continues to increase. So it is kind of like this, and then it increases. So for a very small, or not a very small, for smaller temperatures, you see that in SiC devices, you get a negative temperature coefficient of resistance. Over here, it is completely positive temperature coefficient of resistance. Okay. So, okay. So what are its implications? Can anyone try to attempt what will happen if I have a negative temperature coefficient of resistance? So I will just give you a hint, you can try answering it. So let's say, let me go back to the, yeah. So let me take this particular application, 5 kilowatt, 72 volts. What will be the current? 5 kilowatts and 72 volts. Let's make this simpler. Instead of 72 volts, let's say I take 50 volts. Okay, 5 kilowatt and 50 volts. What will be the current? Current is going to be somewhere around 100 amperes. Correct? Simple, directly. So the current is, if you need devices that are going to carry 100 amperes current, you may not get a single device that will carry 100 amperes. Okay, it's better to parallel a number of devices. Let's say 3 devices in parallel to realize one switch. It's better to parallel 3 devices. Okay, so there are a lot of applications in power electronics where you will try to parallel devices. Okay, so think in terms of that. Let's say you want to parallel devices. Okay, you want to parallel the devices. Then in that scenario, does this have any implication, this negative temperature coefficient of resistance? Any suggestions?
It may damage the switch, sir, in the case of negative temperature quotient. If temperature increases, the current through that particular switch will increase again, and temperature will still increase.
Correct. So, as Ravidas correctly told, let's just forget positive temperature coefficient for now. Let's say that we have a characteristic which is something like this totally, right? Which means that if you increase your or with increase in the junction temperature, the RDS on decreases. Okay. So initially, let's say, let me take another slide. Yeah. So let's say we have 2 parallel devices and they are in the ohmic region. So let me call this as RDS1 and RDS2. Okay. Okay. And total current is 60 amperes, let's say. And due to some mismatch in RDS, right? So it may not be exactly same, right? The RDS may be here and there a few milliohms mismatch. Okay. So let's say RDS1 is less than RDS2. So obviously your I1 is going to be greater than I2, correct? So let's take some number. So let's say I1 is 35 amperes and I2 is 25 amperes. Okay, so this is the initial state of the circuit. That is, the total current is 60 amperes. It is getting split as 35 amperes and 25 amperes because of mismatch in RDS1 and RDS2 initially. Okay. Then what happens? Now, where will the loss be higher? Others, please try to answer. See, we have this particular scenario, that is 60 amperes getting split as 35 and 25. So where will the loss be higher? In device 1 or device 2?
Device 1.
Device 1. Why? Because it's going to be I square R. Correct? I square R, I1 square R1 will be more than I2 square R2. Obviously, correct? So now if the losses increases, therefore the junction temperature will also increase, the temperature of device 1 will increase. So T1 will be more than junction temperature of device 2. So now the junction temperature increases, correct? So TJ1 becomes more than TJ2. If you have a negative temperature, if you have a negative temperature coefficient, It's still there. If you have a negative temperature coefficient, then what might happen is, as the temperature increases, right? So let's say you moved from 0 to 25 degrees. As temperature increased, the resistance still decreased, right? It was over here, now the resistance became this, correct? Resistance decreased. So if the resistance decreases, it will carry more and more current. So the 35 ampere may become 40 amperes and 20 amperes, right? Because the resistance has decreased now. So more current will flow, obviously. Therefore, more I square R loss, more I square R loss means Tj increases. So Tj might go on increasing like this catastrophically. And what would happen is, at some point, the entire device can start carrying the current, correct? So this is the classic scenario of what happens in minority charge carriers like BJTs. So this is why you would have studied that you generally don't parallel BJTs, right? The reason is that they have a negative temperature coefficient of resistance. Okay. But in MOSFETs, you will see that you generally have a positive temperature coefficient. At very low junction temperatures, you have a negative temperature coefficient, but point is beyond 25 degrees or 50 degrees, it again becomes positive temperature coefficient of resistance. Okay. So, yeah, so just an interesting observation that I wanted to discuss with you guys. Okay. And again, if you have to kind of contrast other characteristics, you see over here, reverse recovery time. Why do we get a reverse recovery time? The reason being that you have the anti-parallel diode connected across the source to drain. So if we have to study the characteristics of this device, again DPT is helpful for that. But yeah, if you have to study about it, this diode will also have some reverse recovery time. Okay, you can contrast it over here that while it is 310 nanoseconds for SI MOSFET, silicon MOSFET, it is only 13 nanoseconds. So your reverse recovery losses are going to be much lesser for SiC MOSFETs. Okay, so you see over here it's 4 microcoulomb, that is 4000 nanocoulomb, whereas this is only 35 nanocoulombs, way lesser, way lesser. Okay, for the same voltage rating and current rating, 650 volt 21 amperes, 650 volt 20 amperes. Okay, so this is the advantage you get with WBG devices, wide band gap devices. Okay. Again, a comparison of the device capacitances. You see CISs for a silicon MOSFET, it is 1750 picofarad, it's 460 picofarad. So you can just contrast COSs, you can just contrast and see, right? And one more thing is your device capacitances, you will see that the device capacitances always decrease with voltage. So if you operate the device at higher and higher voltages, the effective CISS is going to decrease. Okay, so you can do faster switching actually with your you can do faster switching at higher voltages, right? Okay, so till this point, is it fine? We have seen a lot of things, and most of them are just for your information. I thought that it's better to have this kind of a discussion rather than just going through theoretical problems, right? Because most or all of the problems, the answers are given over here, and they are kind of self-explanatory. Okay, so that's why I thought it's better to have a discussion. Right. So till this point, is it fine? Any doubt, anyone? Is it fine? Okay. So, if this is fine, I'll just take a 3-minute break. I'll just have some water, and then we can go over to theoretical problems. Okay. We will start off from where we left off in the last class and the last session. I think we were over here. That is which parameter is critical. We decided that while ambient temperature and of course the on-state resistance are kind of very critical. We also saw how gate voltage influences the steady state operation of the device. Right, so we were over here, correct? So we will continue from the third question. And yeah, since they are mostly theoretical, we'll just try to kind of glide over them. But yeah, I'll just give me a break for 3 to 3 minutes. I'll just have some water and then we can just kind of resume. Okay. Yeah, so we'll just resume and see a few problems. Yeah. Okay, so What are the key features of a custom text fixture for surface mount WBG devices? Separation of force and sense terminals, use of alligator clips, multiple source leads for Kelvin connection, and standard TO type package compatibility. So I think we were discussing in the last class as well. That is, you have what is called as a Kelvin source connection, correct? So typically, what you see over here, I mean, this is the symbol for a MOSFET, but physically, if you try to understand it, you will see that there will be a lot of parasitic inductances. Correct? So within the device package, what manufacturers try to do is they try to take a shorter tapping, okay, from here itself. So this is what is known as the Kelvin source. So effectively, the inductance for the gate source path, right? The inductance, if I can draw for the gate source path, will be something like the gate signal comes over here through this inductance and then through the device CGS, correct? It goes through this inductance and then goes through the Kelvin source. It need not go through this particular inductance. So effectively, you're reducing the gate source inductance, correct? I mean, inductance in the gate source path. So for that, you will see that typically SiC devices come with 4 leads, okay? Drain, gate, um, drain, power source, then Kelvin source, and then gate. Okay, so physically you see that the Kelvin source is nearer to gate. Okay, so your gate source can be given across your gate and Kelvin source. Okay, yeah. So A and C. What factors can affect the accuracy of static characterization of power device? So test lead resistance, ambient air temperature, yes. Junction temperature, yes. And gate current measurement, yes. Okay, so let me just go back to the one that I was, yeah. So you see over here, right, there are quite a few transients. So you will see that these transients actually change with the temperature, right? So let's say you're operating at 50 degrees and the other case you're operating at 100 degrees. These transients will change. Okay. Why is it changing? Just to give a perspective, um, see, when the device turns on and turns off, right? So in the last class also we were seeing that the device has 3 particular regions of operation: cutoff region, right? And then what is known as a saturation region and what is known as the ohmic region, right? So in the cutoff region, the device is totally turned off, and in the saturation region, the device behaves like a voltage controlled current source, correct? Right? Voltage controlled current source, and in the ohmic region behaves like a resistor, RDS on. Now the point is, when the device turns on and turns off, you are reducing the gate source voltage and the VDS is going to increase. Therefore, when the device turns on and turns off, it operates in the saturation region. When the device is completely turned off, it's cut off, and when the device is completely turned on, it is ohmic. But when during the transitions, right, during the transitions, the device operates in the saturation region. Okay, so in saturation region, it operates as a voltage controlled current source where the current, drain current is GM into VGS minus VTH. Correct? So GM into VGS minus VTH. This transconductance is a function of the temperature. Okay, this is what dictates the channel current of the device, and this is a function of temperature. Why? Because you will see that I am not able to exactly recollect the formula for this, but you will see that the transconductance is a function of the electron mobility nu, right? The electron mobility is in turn a function of temperature. Okay. It's a function of electron mobility, right? So it's dependent on U and then the width and the area and so on. Okay, I'm not exactly able to recollect what is GM, but it's a function of electron mobility, which is a function of temperature. Okay. So the dash characteristics of a power device describe its behavior in steady state. I think this is quite easy. This is static IV characteristics, right? So in steady state means obviously it is not dynamic, it's not transient or thermal. Okay. A dash can be used to either heat or cool the device by controlling the ambient temperature of its surrounding environment. Thermal chamber can be used. Okay, so if you're wondering about these problems, if you want to have a look at them again, they will be uploaded in the drive. So do you guys have access to the drive? I mean, are you guys able to see it? You can just go through these problems once again because these are kind of theoretical problems. I'm just trying to go a little, just trying to go through these problems. But if you want to have a look at them once again, do you know where these problems are getting uploaded? Where I will be uploading these problems? Okay, so do you guys know, or should I give you the link now? Is it fine?
Yes, sir. Provide us the link.
It's why this time on a second. It's better because like you can look at the problems later on as well. I'll be uploading it in the drive only. So just hang on for a second. Just yeah. So I just given the Google link, so you can go over here and see the slides. Okay. So whatever you're looking for here will be uploaded in a day or two or probably 2 days. Okay. Capacity, efficiency, total capacity, and the brain terminal force with the force and weight sorted together. So let's the device.
Sir, your voice is not audible properly, sir.
My voice is not audible. Now, is it fine? Is it fine now? So, so you had a device something like this. Then have the capacity pixels.
Sir, your voice is breaking.
Okay, my voice is breaking. So just hang on a second. I'll just try to log out and come in again, probably. Yeah, so am I audible now?
Yes, sir.
Okay, fine. Yeah, so I was talking about this capacitance thing that I think we discussed in the last class as well. So this is your CGS, CDS, and CGD. So what they have told is that drain and source. What is the capacitance seen at the drain terminal? So this is your drain. So you see from here, correct? You are seeing from this side, right? With the source and gate shorted together, right? So source and gate are kind of shorted. So source, the gate, and the source are kind of shorted. So you have a direct short between gate and source. Therefore, CGS is no longer in the equation. CGS is out of picture, correct? So if gate and source are shorted, that is gate and source are one terminal, what happens? Effectively, CGD comes in parallel with CDS, correct? So capacitance is in parallel adder. So CGD plus CDS, right? So what is CGD plus CDS? It is basically COSS. Okay. Conversely, if they had asked, right? Let me take a new slide. If you have the same scenario over here, and let's say they are asking you to short the output side capacitance, correct? So they tell the output side capacitance is shorted. So drain and source are shorted together. Drain and source are shorted together, and they are asking you to find the capacitance seen from the gate side. Okay. So what is the effective capacitance C effective? Now drain and source are kind of shorted. So this is CGD, this is CGS. CDS is out of equation because drain source is shorted. So drain and source are 1 point effectively right now. Therefore, CGD comes in parallel with CGS, which means they add up. So CGS plus CGD, which is nothing but your CISS, input side effective capacitance. Okay. Fine. I hope this is clear, right? If you short drain and source, you will see CGS in parallel with CGD. If you short gate and source, you will see CGD in parallel with CDS. Okay. COSS is basically CGD with CDS. CRSS is CGD. CISS is CGD plus CGS. Gate side is the input side, right? So voltage control device. So gate side is the voltage that you control. It's the input voltage. That's why it is the input capacitance. Input capacitance means CISS, output capacitance means COSS. And generally, you will see that CGS is much larger than CDS, and it is much larger than CGD. Similarly, you will see that CISS is much larger than COSS, and it is much larger than CRSS. Okay, just a thumb rule. You see, you take any device, you will see this relation holding true. Input capacitance more than output capacitance more than the reverse transfer capacitance. Okay. So what is the capacitance between gate and drain called? So this is the gate and this is the drain. So this is the capacitance between gate and drain, which is called CGD, or it is also called as a reverse transfer capacitance or Miller capacitance. Okay, or CRSS, we call it CRSS, or reverse transfer capacitance, or Miller capacitance. Okay, CGD. Okay. What does the impedance analyzer measure during open circuit calibration? Stray capacitance, stray inductance, device capacitance, or device inductance? Oh, sorry. Yeah. So the moment you tell it is open circuit calibration, correct? So in order to characterize a stray inductance, you need to pass a certain current and observe what is V is equal to L di over dt, right? But during open circuit test, what you observe is the effective capacitance, how much voltage it is blocking. So basically, it's the stray capacitance that you observe. What are the necessary steps in equipment calibration procedure, open circuit calibration, and short circuit test? So this is something that's common across like all device characterization, right? You take a transformer, you want to characterize it, first you do open circuit test and you do a short circuit test. Similarly for machines as well, you do what is called as the no load test and the block rotor test, right? So no load test is somewhat similar to your open circuit test, and block rotor test is similar to your short circuit test. Okay, again, so this is something that's common. And what is output capacitance? We just discussed this very elaborately. COSS, CDS coming in parallel with CGD with gain and gate and source shorted with gate source shorted. Correct. So you short the gate and yeah. So basically what we did was we short the gate and source, and effectively the capacitance is going to be these two capacitances appearing in parallel, right? CDS and CGD. Correct? Okay. Doing reverse transfer capacitance measurement, Miller capacitance CGD is typically much dash than CGS or CDS. I just told that CGS is more than CDS more than CGD, or ISS is more than COSS more than CRSS. Okay, so let's take an example. Okay, I think it will be better then. I hope my screen is visible. I will go to a GAN systems device. Let's say you take GS. Let's say you take this device. We go to the data sheet. Go down and yeah. See over here CRSS, CISS, COSS, and CRSS. So CISS is 518, COSS is 126, CRSS is just 5.9. Correct? So let's jot it down. So CISS is 518 picofarad. COSS is how much? COSS is output capacitance, right? 126 picofarad. And CRSS is just around 6 picofarad. Okay, so I have given you CISS, COSS, and CRSS. Can you find out what is CGS? What is CGD and what is CDS? Everyone, please. Simple, right? I have given you CISS, COSS, and CRSS. Can you find out what is CGS, CGD, and CDS? Numbers are over here. Just directly you can see and tell. This is for GS 665160, 650 volts, 60 amperes. Can you tell me what is CGS, CGD, and CDS?
CGS is 518.
CGS is
518.
518. Okay. CGD?
CGD is this one, 518 minus 126.
Okay. And CDS?
Yes.
Others can also pitch in. You can also try to tell what do you feel? What is the correct answer?
CGS is 512 picofarad.
Sorry, CGS is
512 picofarad.
512 picofarad. Okay. What about CGD?
C
6 picofarad.
CGD is 6 picofarads.
CGD is 6 picofarad. Correct. And what about CDS?
Is 120 picofarad.
120 picofarad. Right. So this is the correct one. Okay. Why is it so? The reason being that CGSS, see, we just determined how to find CISS, COSS, and CRSS. We know that input side capacitance, that is something you see from the gate side. Just some of the capacitances that are associated with the gate. So CISS is basically simply CGS plus CGD. Okay. What about COSS? You see from the output side, correct? And short the input side. COSS is basically CDS plus CGD. Okay. And CRSS is the reverse transfer capacitance or the Miller capacitance. That is the capacitance that connects your input side and the output side. Input side is gate, output side is drain, right? So what is the one that connects gate and drain? So gate to drain, right? So CGD. So I have given you CISS, COSS, and CRSS. You needed to find what is CGS, CGD, and CDS. So CGSS, from this you can tell that CGS is going to be what? CGS is going to be CISS minus CGD. Okay, CGD is basically CRSS, correct? And CGD is basically CRSS, and CDS is going to be COSS minus CGD. See, this is not given in any problem, but I can assure you this is one of the very simplest questions, but it might come. They might give you some data sheet and tell that, okay, see, this is CISS, COSS, and CRSS. Find out what is CGS, CDD, or CDS. Simple to find out, right? Just remember, not remember, you just know how to find out CISS, COSS, and CRSS. Is this fine? Is this calculation clear to all of you? I mean, all four of you, please. Is this fine? Just you can give a thumbs up if you cannot unmute. Is this fine?
Yes,
How
sir.
did we calculate? I mean, very simple, right? Okay. Now we can just go a step ahead. And I just told you that the capacitance varies with voltage. You see over here, 518 is at VDS of 400 volts. 126 picofarad at 400 volts. 5.9 picofarad at 400 volts. Now the next question would be, see, Over here, the capacitance characteristic is shown in the data sheet. Okay, that is how the CISS or COSS, CRSS are going to vary with voltage. Okay, now you see that at 100 volts probably and 400 volts, the COSS is quite different, right? At 100 volts, it is something else, and 400 volts, it is something else, right? So they might give you this graph and then ask you to find out what is CGD, CDS, and CGS at probably a different voltage level. Okay, so then you should be able to find out, is this fine? At 100 volts means you have to take what is this voltage, or I mean, what is this capacitance? Is this fine? Okay, so I think this is quite clear to all of you, right? So CISS, COSS, and CRSS computation. Okay. Okay, so we'll just move on to the next question. What is the purpose of low impedance path and capacitance measurement? To increase signal strength, to minimize voltage loop, to reduce measurement noise, to improve thermal stability. So the answer is to reduce the measurement noise, because if you have longer and longer cables, right? If you have longer and longer wires, the more it is susceptible to external noises and interference. Okay, right. So what are the key characteristics of the Miller effect? Okay, so this Miller effect is something that you will study in week 3. So I am not going to touch this problem now. Okay, Miller effect you will study in week 3. So we can continue for question number 8. We will see in week 3. Okay. Right, but you did study about gate drivers, right? Do we have time for a set of 5 more questions? I'll just go ahead and we'll just wrap it up by around 8-10 or before that. So what is the primary function of a gate driver in a power conversion system? To convert AC to DC? No. AC to DC conversion is done by rectifiers. We need not have gate drivers for that. To interface control signals with power devices? Yes. You will give the pulses from a microcontroller. So microcontroller will give pulses in the range of 0 to 3.3 volts only, right? Or 0 to 5 volts in some cases. What the gate driver does is it will boost up this voltage from -5 to +15 or whatever as required, -8 to plus or -3 to +18, whatever it is. Okay, boosting up the voltage, providing an isolation, right? Isolation, voltage boost up, right? And gate driving power. All of this is accomplished, and protection, of course, right? You studied about protection and all. So all of these features are done by gate drivers. So gate drivers are going to give you isolation, voltage booster. They will give the required power for the device to turn on and turn off. So that's called the gate driving power, right? Every time the device turns on, it needs some power to turn on. Okay. And that's the gate driving power, and of course protection. Okay. To regulate power supply voltage, no, and measurement of current flow, no. Okay. Which of the following is not a key power device characteristic parameter for gate drive design? On-state resistance, of course, yes, it's a key parameter, and it's a power device characteristic. Breakdown voltage, power device characteristic. Gate threshold voltage is a power device characteristic. But gate resistance value is something that we do, right? Gate resistance you can design, but on resistance, what is the maximum VDS maximum that it can withstand? What is the threshold voltage? What is RDS on? All of these are properties of the device. Properties of the power device. And you can find these in the data sheet. So the consumer cannot do anything, but gate resistor value, it is in our hands. Okay. So it's a design parameter. Okay. Which of the following are components of the basic functional blocks of a gate drive? Signal isolation, yes, we just noted it down. It does signal isolation, right? Gate resistor, no. Gate resistor, as we just mentioned, it is with the designer. It is not into any IC. Okay. And of course, it acts as a PWM controller. Whatever PWM signals you give, it will boost up according to the required voltage level. And of course, it will give you an isolated power supply. I mean, you need an isolated power supply to operate the gate driver. Okay. So gate driver typically looks something like this. Gate drive. So it will be isolated. Okay. And over here, you will be feeding your PWM pulses. There will be PWM pulse, and you need to give, let's say, some power supply VDD, probably plus 5 volts, just for the gate driver to operate, right? And there will be some enable signals and so on. Okay. And on the other side, right? On the other side, you will be getting the boosted PWM or gate signals. Same PWM that you give 0 to 3.3 volts will be boosted to -5 to +18, right? And you will be giving the required gate driver voltage. So you need to specify, like let's say you need PWM pulses from -5 to +15. You need to give +15 over here, right? You need to give -5 over here. Okay, you need to tell the gate driver that this is the voltage I want. Only if you give instead of +15, you give +12 over here, the pulses will also be with respect to 12 only. Okay, so you need to give for the gate driver, you need to give its +15, right? And of course, there will be PWM and there will be the power, whatever is the reference point. Okay. You see, this ground is different than this ground, so isolation, right? And boosting up of voltage. And see, all this +15 volt is with respect to power ground, -5 volt with respect to power ground. However, this is a different ground. We call this as, let's say, signal ground. So your PWM pulses will be with respect to signal ground. Okay. Fine. A good gate drive can efficiently and reliably control power devices under static, dynamic, and fault conditions. Very simple question again. In WBG devices, high dash and high temperature operation become unique challenges. What are the challenges? For WBG devices, they operate under fast switching. So fast switching means turn on and turn off, T on and T off is in nanoseconds. So if it is in nanoseconds, you will obviously be experiencing very high dV by dt and very high di by dt, fast voltage transitions and fast current transitions. What component in a gate drive amplifies the driving capability of logic level control signals, right? So basically it's gate driver IC, right? Signal isolator, no, it will just isolate, right? Not gate resistor and so on. Okay. What key parameters affect switching performance and are critical for gate drive design? So again, CRSS influences the switching performance. V threshold influences switching performance because only after V threshold it will turn on, right? RDS on comes only in steady state, right? Only after the device goes to ohmic region. Right, when the device is in transition region, the device is in the, I mean, saturation region, right? When the device is experiencing transients. Okay, fine. What is the significance of gate resistor? So, not EMI, it limits the current. Yes, it can limit the current, but it doesn't necessarily limit the current, and it controls the voltage level of the gate. No. So it controls the switching speed of the power device. Right? Because we just saw that the device is basically having capacitances, right? It has CGS over here. Okay. Now what you are having is you are having the gate resistor, correct? And you are driving it. Something like this, correct? So during turn on, what I can approximate is that this circuit can be approximated. Oh. So this circuit can be approximated as an RC circuit, correct? There is an R and then there is a C. So this is your CISS and this is your gate resistance RG. I don't know why it isn't coming, but there is some problem, bro. So this is your supply V gate RG and this is your CGS. So this is basically an RC network. Okay. So if you change your R, the profile of the voltage across the gate source capacitance also changes. That is VGS also changes. So the gate resistor controls the switching speed, right? So if you increase RG, then what happens? The RC time constant increases. Therefore, your gate source voltage will increase slowly. So if you want gate source voltage something like this, you can get a response something like this, or you can get a response something like this, or you can get something like this, right? So whether it is underdamped or overdamped, it depends on the gate resistance that you use. Okay, so it controls the switching speed of the power device in how much time the device turns on, right? It is controlled by the gate resistance. Okay, so I think we can conclude till this point. Okay, we will start off from here in the next class. So any doubts anyone so far, or can we conclude over here? Is this
So one
fine?
doubt in question number 3.
Question number 3. Yeah, just a second. Question
So it
number 3
shows
in this one.
yeah,
This one.
it shows
Yeah.
answer B is also answer.
Oh, okay, fine. Just a second. I'm not able to maximize it. Full screen. Oh. Which of the following are components, basic functional blocks of a gate drive? Signal isolator, gate resistor, PWM controller, and isolated power. Okay, so I was talking in terms of a gate driver IC. Okay, but the question is not really gate driver IC. So thanks for pointing it out. So they are asking for a gate drive circuit. Okay, so if they are talking in terms of a gate drive circuit, we can approximate something like this, right? So this might be the gate driver IC. Okay, and then you have the gate resistor and then CGS capacitor, right? So this this gate driver IC is this. Okay. Okay. So your gate drive block, okay, you can tell that it consists of this entire thing till your device. Your device starts from here, right? So till this point. So yeah, if you talk in that terms, then RG is of course included, right? And signal isolation is there from your gate driver IC, correct? So your RG gets included, and yeah, so your PWM, they have written it as PWM controller. So PWM controller refers to the microcontroller, correct? Oh no. So PWM controller refers to the microcontroller, therefore, let me not rub this off, but okay. So your PWM controller is definitely not. So PWM controller is actually your microcontroller. and your microcontroller is giving these PWM pulses. So they are coming from the microcontroller itself. Okay, so yeah, you're right. So PWM controller is not a part of the gate drive circuit. PWM controller already gives the pulses. So gate drive circuit is basically what it does with those PWM pulses. So yeah, thanks for pointing it out. Anything else that we should discuss, or can we close off for the day?
Sir, I have a doubt.
Yeah.
Gate, sir,
Yeah.
you told that this gate, it is different that gate register will control the switching frequency. But the design criteria of the gate register is not with the switching frequency, right, sir? It is told in the lecturer with respect to the switching power, but its design criteria is not mostly about the switching frequency. So,
In question, are you talking about building this one, the system?
sir, your voice is not clear, sir.
So yeah, gate resistor.
Sir, your voice is breaking. I'm unable to listen it clearly.
Okay. Yeah. Yeah. Okay. Yeah. Yeah. Well, are you able to hear me now? And we are actually down. That's we can take it from today's class. Okay. Yeah. Yeah. So we like